Okay, so 13, 1 to 4, the 2025 version, slightly reworked from last time. 1, we're filling in kinetic theory, made up of 3 parts. Part 1, for extra credit, you could say matter's made up of very small particles. If you just said matter's made of particles, I could go with that. They are in constant motion. These particles are in constant motion. That was part 2. And by particles, what do I mean? Particles. Not quite that small. Atoms, along that line, molecules, those kinds of things. The third part is what number 2 is, so you couldn't get extra credit out of that, but you could have gotten 2 extra credit points for part 1 and part 2. 2 is a thing called cohesive forces, cohesion, cohesive forces, both would work. 3 is fluids. Extra credit, most materials expand when they're heated, contract when they're cooled. I would do 2 points for that because there were 2 blanks. The next extra credit one is vibrate. 4 is a thing called convection currents. So if you had one of those 2 words, I'd give you a half a point on convection currents for 4. Bimetallic strip is 5. I'd give you half a point if you had one of those words for bimetallic strip. 6 is surface tension. 7 is volatile. 8 is adhesion, adhesive forces, something like that would work. 13 is capillary action, or no, 9 is capillary action. I'd give you half a point for one of the 2 words. 10 would be down. 11 would also be, it goes down. Those both go down. Question about scoring that.
What was 9?
9 is capillary action.
What was 11?
11, it's going to decrease, go down, be lower. Wait. No, that's backward. I gave you the wrong answer on 11. It's increased, it's up. Be higher. What?
For the second extra credit round, would you take the things speed up when heated and slow down at home?
No. Not unless someone can find that in the book. That is true, but that wasn't like covered in that section, I don't believe.
What was 4 and 5?
4 is convection currents. 5 is bimetallic strip. Question about any of that? Well, here's good news for your chapter, which I already told you another day recently on this present year, is there isn't really math problems in this chapter. There's not an equation, so there's not homework for like 2 days. There is a chapter review eventually that will incorporate some math somehow, but it doesn't have to do with really math from this chapter so much as they must bring back some old math. People have their own quizzes back, 13 1 to 4s. Okay, so the good news is there's not homework. The bad news is there's like a boatload of things to try to absorb. So here's like a million notes to take, and this will turn into questions for next time. Just take the notes for now, and then I'm going to give you a paper that looks like this, that has a big empty space on the top, and it's misnumbered because this year I redid this quiz. But tomorrow, this missing empty top, it has like 14 points worth of stuff, but it'll only count out of 10 this time. I'll do some stuff as extra credit again like I did today. But as you read from 5 to 8, you can take notes on like up to 14 facts that'll appear tomorrow. And then the stuff I'm describing to you now, this will show you exactly how the questions become relative to what I say. And that if you take the notes, you have the information that you need. So here's some thoughts on this. Is the kinetic theory, it's important to know it was invented to explain the behavior of matter. Why does matter do what it does? but that's already typed by me. But tomorrow that'll become a question. Why is the kinetic theory a thing? It's to explain the behavior of matter. We already said earlier, matter's made up of very small particles. If you didn't already say that, or have your grading friend fill that in, Matter's made up of very small particles. They are in constant motion is the second part of that theory, and I'm sure that'll appear tomorrow. And then I believe you'll be asked about a certain kind of motion because a certain scientist confirmed part of this theory. Anybody have reading memories of a scientist that confirmed this part of the theory about the constant motion? Yeah, it's called Brownian motion. So jotting down Brownian motion is the name of this motion would be good. And then Robert Brown was the guy who confirmed that part of the theory. So knowing about Robert Brown and Brownian motion, some of that's going to factor in somehow tomorrow.
What was the first part of that?
First part is matter is made up of very small particles. Second part, they're in constant motion. Side note, Robert Brown confirmed that part of it, and they named this motion Brownian motion after him. My best way to explain this to you, the book explained it to you, and I'll just steal what they said, is the idea of like the way that perfume, or in the boys' world, Axe body spray, fills a room. Right now, this room is full of all kind of air molecules. If you introduce some perfume or Axe body spray molecules, all of these molecules are in motion, they're all bumping into each other, and they're going to eventually kind of collide and spread. So sooner or later, if we sprayed something up here, it would make its way through maybe the entire building, depending on how much Axe body spray we dumped on the hallways. But it's gonna spread because of this Brownian motion, this constant motion of molecules bumping into each other. Cohesive forces, I have jotted down some side notes here around number 2 on these cohesive forces. They're it's what makes objects hold their shape. So what kinds of things would have very strong cohesive forces? Solids. Solids have a very strong cohesive force going on there. This book is a solid. That book isn't really falling apart or going anywhere. Solids have very strong cohesive forces and hold their shape. What would be sort of like medium? Liquids are medium. If we spilled some water, it's gonna like spread and lose its shape somewhat, but not ridiculously. What would be the weakest? Gases. There was a synonym for these that might make the next quiz, a synonym for cohesive forces. It's the last name that came in 3 chunks. Van.
Oh, it's like Van
Der.
Yeah.
Walls. VANDERWAALS. These cohesive forces can also be called van der Waals forces. But to recap, cohesive forces help things hold their shape. They can also be called van der Waals forces, VANDERWAALS. And if we tried to break it down, liquids are medium, gases are weak, solids are strong on these kind of forces. Fluids, I didn't have anything else to talk about there other than gases, liquids, both considered fluids. They're things that flow. Expand when things are heated. I have a side note for this. There's 2 reasons why things expand when they're heated. One is because you get bigger rebounds on the collisions. So if you have more heat, you're going to get more motion, you're going to get things bonking into each other at higher speeds, and the rebounds are just going to go farther. Some of you that are basketball players, you shoot a nice soft shot in there, the rebound doesn't go so far. You fire in a pretty heavy duty brick, that rebound is going to go far. But if we get some heat, some velocity on these particles, the rebound is going to be bigger on the collisions. And then the other factor is that cohesive forces are less. If these molecules are zipping by each other at great speed, they just have less chance to be attracted to each other because they're too busy zipping. But why things expand when they're heated is greater rebound on collisions and cohesive forces less when they're hotter. The book explained, they sort of pointed this out by saying, think about telephone wires. I don't know if you pay attention to your telephone wires, but in the winter compared to the summer, what's the difference in your telephone wire actions? Shapes. Do you ever pay attention to utility lines at all? So summer is hotter, what would it do there? They'd expand. So if you had some sort of wire that expanded, what would that make it do in the summer? Yeah, it gets sort of droopy. But in the winter, it would contract, which would make it like straighter. Bridges do that. Roads do that. Sometimes you drive along the road and you're hearing like that, all that kind of stuff. It's because in the summer, what are those panels of road going to do? They expand, so they have to leave some space. And in the winter, they're going to contract to like, you'll have to leave that space in the winter, so in the summer it'll like expand and fill the shape. Unfortunately, in the winter, when ice gets in there and freezes, it can like bust up your roads. But expand, contract. Vibrate, I have no comment on that. That's just a standalone question. Convection currents, jot down there, air around a radiator is an example of the convection currents. I don't know if any of you have experience with radiators. My Penn State dorm room was based on a radiator system. The elementary school used to be based on a radiator system until pretty recently. Radiators heat stuff based on like basically water and steam. That you're sending hot water through your building. It comes out of a thing called the radiator, and the radiator emits this heat. And hot air tends to rise. The cold air zaps in there, and then the cold air gets heated, and then it rises, and you get sort of this churn of the air getting heated, and the air naturally just sort of starts to flow around your room. When I was a freshman, there's supposed to be a little knob you use to adjust how much the radiator is getting, and my knob broke, and foolish freshman that I was, I called like maintenance to fix my knob. How do you think that went for me?
It's a lot of not good.
Not well. They never showed up. They didn't care. So the heat just ran full bore in my room. It was a sauna like all the time. So when we wanted to sleep, we'd have to open our door to the hallway, open the window in our room, put a fan in the window to zap like the 30-degree outside air to our room and chill it down to like 30, close the door so people wouldn't prank us, and then go to sleep. And about 5 hours later, in the middle of the night, it would be like 9,000 degrees again, and we'd have to repeat the process. It was a good time. But radiators, convection currents. Bimetallic strip, follow up on bimetallic strip, it would be like an older thermostat. We have a couple in this building in some of the classrooms where they have those thermostats that you turn the dial. Most of the world has gone like digital thermostats. But there's like a dial you can turn, if you know what I mean, that kind of thermostat.
Like Mr. Cummings' room.
Yeah, Mr. Cummings' room has one. So what's going on is you have these two pieces of metal like this, and when they get hot, they'll bend one way, and when they get cold, they bend the other way, because they're two different metals and they have two different like expansion rates. So what you have is like a contact point on one side, so that when it bends this way, it touches something that says too hot, turn on the AC. And on the other direction, there's a contact point that it touches to say too cold, turn on the heat. But when you're doing that radiator or that thermostat, there's this bimetallic strip that's like part of that project. Surface tension, I'll draw you a little picture to explain surface tension. This is why bugs can walk on water and why leaves don't sink, is if there's some sort of water molecule right here, it's attracted to the other water molecules. One to its right and one to its left, and those attractions basically cancel out. It's also attracted to the stuff under it as well as the stuff above it. But in the middle of the water, that stuff is also gonna cancel out. If you get to the top, you can still be attracted right and left to cancel out, and you're still attracted down, but there's no attraction up. So this very top level of attraction down makes the very top level of water like a little bit more dense, a little thicker. So if a leaf lands on that, it'll just sit there. But if it punctures in a little bit, then it's gonna sink. Once it's in, it's gonna sink. But as long as it's on top, it's got that surface tension that's gonna help it from dropping. So I think there's a follow-up on that tomorrow. Something about there's attractive forces, more attractive forces down than up, or maybe that there's attractive forces everywhere except up, and it makes the top layer more dense. Something like that is on there. Volatile liquids, just I have a side note on volatile liquids. They have weak cohesive forces. Something like rubbing alcohol is like that. It evaporates super fast. So if you have like rubbing alcohol on your arm and then it evaporates super fast, what does that make for you, feeling wise?
Burns.
Then it's going to feel cold. It's going to like chill you down. So nobody has rubbing alcohol experience, I guess. Adhesion is attraction with different types, so that speaks for itself. Capillary action. Example of capillary action they talked about in the book was paint in a paintbrush. The paint, if you give paint a paintbrush, the paint is attracted to the other paint, but the paint is more attracted to the paintbrush, and so the paint soaks into the paintbrush. That this capillary action is the concept on which paintbrushes are like able to scoop up. Evaporation we just talked about a little bit with that rubbing alcohol explanation. So when evaporation occurs, temperature goes down. So let me make sense of this for you. If things are evaporating, that means a liquid is turning into gas. Who has more energy? Liquids or gases? Gases, because gases generally exist at a higher temperature. It takes some heat for turning liquids into gases. So what's going on here for evaporation, boiling, those kind of things? The highest kinetic energy particles are escaping. The highest kinetic energy particles are the ones that make the jump. What is temperature? Definition from the test we just did. Average KE. So if your highest KE people leave, the average is going down. It would be like if we showed up for school tomorrow and we look at our physics average and we took the top 2 grades and say, we don't want you in this class anymore, you're out of here. Our average grade would go down because we lost our best people. That's what's happening with evaporation. The highest energy particles are jumping, so the average has to go down. Pressure increased means that the boiling point is going to go up. An increase of pressure means it's harder for those particles to escape, which means it's just going to boil not at 100 but like 110. If we went pressure decrease, and the question tomorrow on the quiz might be pressure decrease because I was crossed up when I first said that. A pressure decrease would make the boiling point go down. Where on earth do you have lower pressure? High altitudes. So if you went to Denver, Mile High City, water wouldn't boil at 100. The pressure is lower, so it's easier for those molecules to escape. You might be able to boil water not at 100, but at like 85, something like that, 85, 90 degrees. So would your food take longer or shorter to cook? Longer.
So right.
Why would it take longer to cook your food if water's boiling at 85?
It's not hotter.
It's not as hot. Boiling doesn't do anything for your food. Heat is what does stuff to your food. So if you're in Denver and your water's boiling at 85, it's going to take you longer to cook your food. That's all we got. Somebody could cut that. Here's your paper that shows you exactly